Perfect. So today it's our great pleasure to welcome Dr. Mehrad to share his research and insights with us. Dr. Mehrad is a stunning scientist at the Acceleration Consortium. His research is focused on applied AI and automation in self-driving chemistry labs. And beyond his technical contributions, the Mehrad I know is also a passionate advocate for open access science, and he also has pioneered the development of several impactful tools that advance scientific discovery. So Mehrad, we are excited to hear about your groundbreaking research, and the floor is yours.
Thank you so much for the introduction. Hi, and good afternoon, everybody. So today we're going to be talking about how we can incorporate more domain knowledge into data-driven workflows. So I'll share some work that I did during my PhD research, and then we'll be mostly talking about the work that I'm doing currently at the Acceleration Consortium in the context of self-driving chemistry labs. So simulations implement the forward process. That is, given some input physical parameters to a model, you can generate synthetic data. Now, this data mostly comes from physics-based models, which are essentially based on first principle calculations and conservation laws. So as an example, you can, if you want to predict fluid flow behavior, you can run a computational fluid dynamics simulation based on Navier-Stokes equations, which are essentially conservation of mass, momentum, and energy. Or you could run a molecular dynamics simulations and solve the solve Newton's second law of motion numerically. So regardless of the complexity of these models, they're still a proxy representation of the natural phenomena that is happening, mostly because of the simplifications we make to be able to solve these models numerically. They're also too time-consuming to evaluate. Now, what if I told you we're actually interested in the inverse format of the problem? That is, given the data, can you give me the best fitting model? So this is the main idea behind data-driven approaches, which act as a surrogate to the physics-based model. They basically work based on identifying patterns in the data, and that data comes from real-world experiments or high-fidelity simulations. So despite the advantage of running at low compute cost, they lack interpretability and intuition for the underlying physics. So a great part of my research is kind of focused in combining the two words in the context of physics-informed machine learning. So when it comes to physics-informed machine learning, you probably have seen this video. It's essentially the famous classical problem of harmonic oscillator being solved with a deep neural network, where we actually have the partial differential equation used in the loss function. This is how we incorporate physics into the model. So like, can somebody tell me what is the main advantage here based on comparing like the second and third panel together? Any ideas? Don't everybody speak at once.
I think for the okay, yeah, I'll mute myself. I think for the neural net, we can see it does a good prediction on the given training set. Well, it doesn't generalize to these unexplored areas. But if we combine the physical informs like these heuristic functions with the neural net, actually we can do both. We can achieve both good fitting quality in the training, like in distribution and out of distribution. Is that right?
Exactly. So somebody also in the chat, Rafael, mentioned that the search space has been constrained. Yeah, both what you said is correct. Essentially, we can generalize much better without worrying about the IID assumption. Now, what is IID assumption? Essentially, IID is independent and identically distributed. So this means that each sample comes from the same probability distribution, and also the probability of each sample is actually independent of the other sample. As an example, let's consider like a coin flip. So no matter how many times you flip a coin, let's say you flip like 6 times, you get like heads, still for the 7th time, there's a 50% chance you're gonna get tails. So that is independent of the previous ones. So physics informed is very interesting. So this is one interpretation. There are like two more other interpretations. This is the most commonly used interpretation for physics informed. The other two ones here where we incorporate physics informed features into the model. This is something I'll talk about shortly. And then there's also physics informed data. And physics informed data is essentially like data that comes from physics-based simulator. As an example, like QMOF data set contains about like 135,000 quantum mechanical properties that are based on DFT calculations. So that is also my interpretation of physics informed. But as I said, the first approach where we incorporate like the actual theory-based equation into the the loss function, that's the most defined definition. So I'll talk about like the history of machine learning and how like essentially domain knowledge was integrated. So this history can be summarized by two words, emergence and homogenization. So emergence refers to the system's behavior, as in emergence refers to the system's behavior, which is often imposed indirectly, and homogenization refers to the consolidations of methods that allow us to build different machine learning algorithms over the wide variety of applications. So it all started with machine learning in the early 1990s, where the model was able to learn how to perform a task based on some training data. And this how effectively emerges from the dynamics of learning. So with this was one step towards homogenization, because using simple generic algorithms such as like support vector machine, logistic regression, random forest, you could accomplish different tasks. Now, but the problem came in where people wanted to deal with semantically complex problems in natural language processing or other problems in computer vision, where they had to do feature engineering, essentially define how they would input the features. And this is primarily how they incorporated their domain knowledge into the workflow. So feature engineering, not sure if you've done it, it's a very long, tedious process and takes a long time, which actually brings us to the era of deep learning, where we had we could actually input raw data into the model and have high-level features be learned by the model at training time, thanks to a trainable embedding layer. Now, this is another step towards homogenization, because using the same deep neural network architecture, you can actually accomplish different tasks. As an example, this is a work I did in my PhD. This is a work I did at Toyota Research Institute. You can actually see the similarity in the architecture here. So in the top, we're actually using a bidirectional LSTM to learn distance-based dependency information between the amino acid residues, mapping the actual peptide sequence to the biological activity. This includes like solubility, hemolysis, or a resistance to non-specific interactions. And here we actually incorporate not physics, but mostly like biophysics knowledge, in a sense that they're directly adding the frequency of amino acid within the sequence after the bidirectional STM layer. So the problem with so one advantage of deep learning is that thanks to having more parameters, it generalizes better. But one disadvantage is that it needs a lot of domain-specific data to train on. And this was solved with transfer learning, which brings us to the era of foundation models. So foundation models are trained on broad data, and then they can be fine-tuned on downstream tasks. And this brings us a lot of functionality, in a sense that they actually homogenize themselves. And they can, so with just training the model on broad data, you can actually see capabilities like in context reasoning emerge. So I will be talking more about how we are actually using foundation models to perform different like chemistry-related tasks. So before that, I want to take your attention to this. And this is actually a meme I found really relatable. And This is relatable in two senses. One is that this expectation of people from AI sometimes is, I found it unreasonable in the sense that we don't necessarily need to use AI for everything. And when we do, we gotta make sure we understand the limitations. So I won't be talking about like bias or reliability. Like dual usage is one major area of research, which is very interesting. I highly recommend that you look into it if you're as interested as I am about this concept. But I want to talk about uh, reliability as an example. So you probably have seen examples like this appear on social media and people claiming that, okay, yeah, this is going to be the smartest model, but it cannot do simple math. So probably you have maybe tried this on your own to see if it happens. So I'm just curious, does anybody know why something like this is happening in the chat?
I think it's related to how the ChatGPT, the large language model, deal with these descriptors, right? It doesn't interpret these math symbols as a human does. So because I know was a issue with ChatGPT is like when you ask it, like 11.11, it is larger than 11.7, but it will tell you no. Yeah, it is.
Mhm. Yeah, so you're right in a sense that it's so this comes from based on how the model was trained. So the model is actually trained to predict the probability of the next output token within a sequence, and it's actually not trained to do math. It can uh, possibly do some math, but when it comes to like integer multiplication or other math operations, it is bound to fail. And this is kind of why we augment it with augment the large language model with a calculator so that we wouldn't make these mistakes. So I want to talk about how we can actually augment a large language model with different tools. So this is actually what we're doing at AC in the context of self-driving labs. So we are considering using AI agents, which are powered by a large language model at the core, to be an intelligent orchestrator to a self-driving lab to facilitate flexible automation with built-in domain knowledge. So the flexible automation comes in where we don't necessarily want to hard code everything because we would like our workflow to be simple, and for future changes, of course, uh, we don't want to like break things if we are asking for a simple change. So with this, we can actually augment the LLM with a set of tools. These tools will allow it to make more chemistry and physics informed decision, as in like interact with the robotics API in the lab, as in generate KaiDL code on the fly so that robotics would just input new parameters in their KaiDL code and operate. It can be interacting with an OpenTron in the lab, or when it comes to safety and ethics, we would like the workflow to actually work with safety concerns in the lab in a sense. And let's say carbon monoxide concentration in the lab exceeds a certain threshold and you have a faulty PM hood, we would like the information from the like the sensor in the lab to be passed on to the model, to the safety tool so that it would abort the experiment if needed. In terms of ethics, as an example, this is like a very new area of research. And the main idea is that, let's say we want to use a large language model to uh, uh, essentially high throughput organic frameworks or carbon capture applications, but what is the carbon footprint of running that large language model in the back end? And does the trade-offs even make sense for the in silico design part? So now I want to take your focus to the next two tools, which are the main purpose of this talk, where we incorporate physics-informed and chemistry-informed knowledge into the workflow. So the physics-informed part comes where we are more interested in theory, not necessarily DFT, but any theory-based calculation you can actually incorporate into the model. And if that is too expensive to evaluate, you could actually use the next best thing, a surrogate model that has been already trained on the property of interest. And you can actually run the cheap to evaluate inference model on low commodity resource. And then within this workflow, you could have Bayesian optimization so that you can do an efficient exploration of the search space. And for the chemistry-informed knowledge part, this is essentially retrieval augmented generation from different resources, from online databases to internet to locally stored PDFs or even like papers from preprint servers. So I'm kind of exploring each of these tools at a time, putting these small pieces of the puzzle together. So I want to take your attention to tool 5 and how it works. So this is actually an agent I developed. It's called Eunomia. Eunomia is a Greek word for goddess of stability. And Eunomia is helpful for using existing knowledge from, essentially extracting existing knowledge from scientific literature, scientists, and internet all together within one tool. How this works is that, again, we augment the LLM with a RAG tool. This is retrieval augmented generation based on maximum marginal relevance search so that we keep diversity in the answers we get from these documents. And we sort of incorporate our own chemistry-informed knowledge into the workflow as well. And I'll talk about that shortly. How it works is that in a very simple way, you just give the model your document as a PDF or XML. In this example, we are interested in water stability of MOFs, and we want to do like a ternary classification, stable, unstable, or not provided if the paper does not contain that information. So the chemistry-informed knowledge is actually incorporated into the model very simply in natural language text. And for water stability in specific, this is actually like a vague concept. Different scientists have different interpretation of what water stability means. Some say that I want no loss in crystallinity. Some say I don't want it to be insoluble in water. Another person say I want it to survive a boiling environment for like 7 days, or like different interpretations. And when you actually want to extract that information, make your own data set, this this can be like tricky for you if you want to do exact word matching. So for this purpose, we actually have this agent doing an iterative chain of verification on its own based on the exact sentence it gets from that scientific literature. And it would use that sentence to assess whether the model actually made the correct prediction, in a sense that was the context it actually made the decision based off, is it talking about water stability or not? And with that, you can actually make your own customized data set. This is mostly machine learning ready. For MOFs, it could be tricky because you actually need like the chemical structure in a CIF format. But for other properties, you can also use it and can be valuable. So you can actually pip install Designer, and if you're interested, it's also hosted on Streamlit. We can actually show, I'm actually going to show quickly how it works on Streamlit. But before that, I want to show you how the iterative chain of verification works. So suppose we have the human expert chemist on the left, and we have the AI agent chemist on the right, and we want to see the conversation between them. So very simply in natural language text, we ask the model to read the paper, find water stable MOFs, and justify your reasons. The model goes and reads the paper, finds that there are 2 MOFs there. So it would label water stability, if you follow my cursor here. And then it will also provide a justification for the water stability label. And then it will evaluate the reasoning on that and sees that, okay, for the first example, this is actually talking about thermostability and not water stability. So it will automatically exclude this data point. For the second one, it will actually keep it. So I want to show you how this actually works. So this is the app on Streamlit. So I'm gonna say that this was developed way before you could simply upload like a PDF document to cloud, or I mean, actually cloud was not even there, to like OpenAI, like ChatGPT. So here I'm actually putting the material type, and I put in some information on what water stability. No, this is actually the input prompt where I'm asking it to uh, give me information about water stability. And here, this is where I put in the design guidelines. This is like extra context I give in a sense that what water stability means. So you could try this with other properties. We have like examples on the GitHub repo. This code is also open source. Feel free to use it. So after this, I will also tell it how do I want my final output to look like. And then I've already uploaded the PDF. I'll just click extract information, and shouldn't take too long. So sometimes the iterative chain of verification has to go back and forth, but here's the answer we get for all the MOFs mentioned in the paper. And this is a justification for them based on exact sentences that come from the research paper. And this is actually the DOI for the paper. Okay, so moving on to the next one. So you don't necessarily need to have locally stored PDFs. You could also deal with papers that are coming from preprint servers. This is actually like another workflow that is hosted on Hugging Face, and similar idea, but you can actually do a quick search on papers that come from arXiv, ChemArchive, bioRxiv, and medRxiv. In the interest of time, I'm just gonna show you this video real quick, and as long as you have a valid OpenAI API key, you can use it. So I'll put in reticular chemistry, MOF design, and I'll ask it to give me 6 papers, searching from arXiv and ChemArchive. And then I put in this question, why is reticular chemistry important? And then I put a limit on the number of words I want to have in my answer. And after a short time, voila, we get the answer here. And we actually get exact references for each sentence that we get here. So yeah, let me find, I have a lot of tabs open. Let me find my screen. Okay, great. So going back to this figure, you might want to ask me, okay, so why do we care about like that domain knowledge is coming from the literature and how we can actually use it? So I'm gonna show you our latest work at ACE, where we use tools 4 and 5 together. And this is actually another agent that I developed. It's called Designer. And the idea is that we wanna use an AI agent, a chemistry-informed AI agent for design of small molecules with desired target properties. How it works is that in a very simple way, you input a small molecule in natural language text, and I actually use SMARS, which is the most like common textual representation for a small molecule, and then ask it to decrease or increase the property. This property can be up to you. We've done benchmarks on like ligands, surfactants, even like peptides based on the peptide sequence that I'll just talk about shortly. So in the backend, designer goes and reads the literature for us. This again can be based on different resources from online databases, internet, locally stored PDFs, preprint servers, and finds out some guidelines on how to interact with the property. Let's say you're dealing with like binding affinity, which functional groups are actually helpful to increase binding affinity of a ligand against a protein target, or it can be other properties. And once it has this information, it would generate a new molecule by making changes to the initial molecule you suggested. And then we do a quick check on feasibility and synthesizability. So feasibility is based on simple RD-kit sanitization, making sure the valence rules apply. And synthesizability, essentially, this is based on famous like synthetic accessibility score or synthetic complexity score, or if you're dealing with like a ligand for drug discovery application, you can do like QED, quantitative estimation of drug likelihood, which is a set of 8 physiochemical properties, such as molecular weight, number of hydrogen bond donors, acceptors, and a few other ones. And once we actually do this, once the agent does this assessment and make sure the new SMARS is valid, it would start evaluating the molecule on the property of interest. And this is based on the domain expert model. So you could have a physics-based model here making prediction, but for the purpose of saving time, I actually just use I use the data-driven model as a surrogate so that we can just use the chip to evaluate the inference model. So this brings 2 advantages to you. One is that you don't need to reinvent the wheel. So you can use the state-of-the-art predictor for your property of interest. It's just a matter of throwing a Python decorator around that function and feeding it to designer. And you can do uncertainty estimation. Let's say you can do an ensemble of surrogate models making prediction, and this will allow you to account for the epistemic uncertainty that comes with each prediction. So steps 1 to 3 are actually the closed loop version of the model, meaning that the model would just do everything on its own. But we also have step 4, which is optional, allowing real-time human AI collaboration, where a domain expert scientist can literally talk with the model as a voice message, or send a send a message in chat, and iteratively update design guidelines and give feedback on the previous designs of the model. So I want to spend some time talking about how we actually benchmark designer. So we generated 1,200 molecules across 3 different diverse applications, predicting critical micelle concentration for a surfactant, that's task 1, predicting binding affinity of a ligand against WDR5 protein target, which is a protein that regulates cell growth. And this is based on docking score. The lower the docking score, the higher the binding affinity, and also CO2 absorption capacity of the organic linker of a MOF. So we here can see the success rate of the model in terms of valid molecule generation based on the design guidelines. And we considered an ablation study having the standalone state-of-the-art models, GPT-4o and Cloud 3.5 Sonnet, and seeing how they would do without the mentioned domain, without the mentioned domain knowledge that comes from our RAG tool. And you can actually see the importance here comparing like baseline with the domain knowledge. So 3.5 Sonnet was much better compared to GPT-4o, not just in terms of molecule generation, but also in terms of generating better molecules at each iteration with better target property. So you can see the success rate on the right. And also, we were interested in identifying to what extent can we have improvement. So for tasks 1 and 2, we are actually working in log scale, so you can actually see orders of magnitude improvement with the help of domain knowledge with like Cloud 3.5 Sonnet actually. So I want to show you how the closed loop version of the model works. And this is the workflow that we have. On the left, if you follow my cursor, we have the initial molecule that we start with. This is the organic linker that we start with. And we make prediction for the CO2 absorption using an ensemble of mob formers that this is actually based on Amir Barati's work at Carnegie Mellon, but I fine-tuned their model against the HMOF data set. So this is CO2 absorption at high pressure, and this is where the uncertainty estimation comes from. Very simply, in natural language text, we ask the model to keep the molecular weight lower than 600. Also, we ask it not to add any functional groups like fluoramines that could possibly cause instability in the molecule. And you can see how the model progresses here. So from the top, it will start reading a literature, and this is based on a set of, I think, 4 locally stored PDF that will help the model understand which guidelines are important uh, for uh, uh, for increasing CO2 absorption capacity, and then uses it to make updates. So you can see the changes happening here one at a time. Changes are accepted if we have an improvement in CO2 absorption capacity compared to the baseline molecule, which is the initial molecule, or are rejected otherwise. And you can actually see that compared to the initial molecule here, we have about 100% increase in CO2 absorption capacity comparing these two values here. Okay, now I want to take a moment and show you how this can actually work with the human in the loop. And we're going to see how we can design like a ligand so it has a higher binding affinity against WDR5. For this purpose, I'm actually going to show you my chat messages with the model. So this is, I'm not going to run this right now, but just showing you how this works. So Designer is pip installable, but for the sake of more like user friendliness, I've actually integrated it within Acceleration Consortium Slack workspace. And this means you can talk to the model, like even voice message it on Slack and ask it to help you with designing a molecule with desired target properties, as long as you have the right surrogate model here. So very simply, I'm going to zoom in a little bit. I ask it to make changes to this initial molecule so that it has a higher binding affinity against WDR5. I ask it to suggest 3 molecules, but also keep the molecular weight lower than 600. So this is actually an initial hit for WDR5. And based on this information, designer will go and do a quick literature review for us. So this is only based on a one locally stored PDF. And from this paper, and this is actually the DOI for the paper, it finds out that, as an example, introducing an electron withdrawing group such as benzamide is helpful, or introducing an amino group is helpful. You can see all the possible adaptations you can make. And after this, it will do a quick evaluation of the initial molecule. So this includes evaluating SA score, SC score, QED, and the molecular weight as well. And then it will evaluate docking using our surrogate model, which is Mina, and then gives you a visualization of the molecule. This is still within the one initial prompt I gave it. And then after this, based on the design guidelines, it will add some suggestions that it can do. So here are the suggestions for the new molecules. You can actually the changes for each one. And then it's asking me whether or not I'm happy with this change. I give it a go ahead, and then I will iteratively evaluate like each of these molecules, evaluate SA, SC, QED, molecular weight, and also the docking score. So out of these molecules, you can actually see that the first molecule, we went from minus 6.7 docking score to minus 7.3. So we want to increase binding affinity. That means we want to decrease the docking score. So out of these molecules that you see here, this is also like the visualization. I actually, and also this is like the final summary. It will give lots of text here, so hope you're following. I ask it that here's me actually sending a voice message to it. Like the second molecule, could you add benzamide to the center? And it will follow those steps and essentially introduce like a benzamide to the center. So one thing with benzamide here, benzamide is actually added here. And one thing with benzamide is that because of these benzene ring, they're likely sabotaging solubility, and we also really care about solubility. So at the next step, I actually ask it to improve solubility. So here, I ask it that, okay, I also care about the solubility of the molecule. Could you look up online on identifying ways we can improve solubility while preserving that high docking score? So this is a simple internet search using SERP API, and the model does a quick search, essentially finds that adding like polar functional groups is helpful, and then it will start making changes based on those suggestions. So the initial solubility of the molecule was, I'm trying to follow it here. The initial solubility, I think, was minus 6.1, which is a really low value. And then it will start like making changes. And here you can actually see the change in solubility for the three molecules it suggested. Also, you can see the docking score as well. So while improving solubility, we actually, I think we did improve docking score. Yeah. And then after this, I mean, this is actually only like a limited number of prompts I gave it, but then again, I'm actually not a medicinal chemist. I've worked with great ones, but imagine the great things you can do if like an experimentalist can work with this, just transferring all their domain knowledge, like years of experience in a wet lab into the model. And this is very much important in terms of synthesizability, in a sense that we basically just use a simple quick score like SC score and SA score to do an assessment of synthesizability. But if you like ask an actual medicinal chemist, or like, I don't care about these values, like I need to be able to synthesize in a lab. And this is where like forward and backward retrosynthesis steps become of importance, not to mention the availability of building blocks. And finally, I actually ask it to report all the tools it has used and if there are citations saved. So this is just for transparency of the transparency on which tools the model used. And you can actually see this is like the paper we did like a quick rank from for the design guidelines for checking validity of the ligand. So there's SA score, SC, QED coming from these papers. For predicting docking score, that's coming from Autodoc Vina. And for predicting solubility, this is actually a model I trained using an IBM embedding. They have a large encoder-decoder model that kind of worked well because I didn't need to do much fine-tuning, and I could actually predict solubility. So yeah, with that, I think the main point here is that there are like many different ways that you can like incorporate domain knowledge. And I'm very much interested in like flexible ways, as in like people don't want to bother with pip install. This is kind of I guess this is why people are becoming a lot more interested in like chatbots. But like domain-specific chatbots that can perform like complicated like chemistry tasks, I think would be of very much interest in the near future. So I'd like to take some time to acknowledge the great people I've worked with, and most of the projects I mentioned has been through collaboration with these incredible people that you see here. And with that, happy to answer to any questions. Thank you for your attention.
Thank you so much, Mehrad. So I believe there's some questions from Rafael in the chat.
Okay, sure.
Yeah.
Let me make
Yeah.
this bigger.
Yeah,
So
hello. So, yeah.
Hi.
Hey, hi. Well, first of all, incredible presentation. I really enjoyed it. I'm really interested in how LMs can actually give them all well used domain knowledge. And I had a question. First is how to deal like with hallucinations.
Sorry, is it just me or your voice is echoing for everybody else too?
No, I'm also hearing the echo.
Can you hear correctly there?
Still echoing. Is it just me, Franzi, or?
No, I'm also hearing the echo. Yeah.
Okay.
So I think.
Not
Let
sure.
me remove
Maybe there's something wrong with your microphone.
Or will you also know from my side as well?
Yeah, sure.
Oh, it was working fine now.
Do you hear me well now?
Yeah. I think you have your mic on still there.
Can you hear me now?
Yeah, better, much better.
Okay. So first of all, I wanted to know, how do you deal with hallucination? Sometimes LLMs have that problem. And for example, when you get the references of where the information was retrieved, sometimes the LLMs can give you references that are actually not the correct ones, or they can actually give as output information that it looks like that it is actually correct, but it is not. How do you deal with that? How did you train, or did you fine-tune the LLM, or how did you deal with that?
Yeah, sure. So I'm gonna answer your question in two different aspects. Like one is the small molecule generation, one on the rank part. So on the rank part, yeah, you're right. If you just ask ChatGPT or any model to just give you some like references for some information you're looking for, you're most likely getting some DOI that does not exist. Yeah, that is the hallucination that can happen. So that's kind of why we define these tools and augment it with the LLM so that we just reduce the likelihood of having those hallucinations. So this is in terms of rank part. So when you provide that context, you're like you're kind of instructing LLM to be specifically looking at that context when it generates the information, not just the broad training data. And also on the small molecule generation, I'm not sure if I should call this hallucination, but when it came to complex chemistry tasks, and when I say, I mean, actually not complex, for synthetic chemistry might be simple, as in like move this functional group from like ortho to like the meta position of the ring, we could see that the LLM would struggle a little bit and kind of needed going back and forth a little bit because it was not, this was like beyond what was in the training data, and this was more domain specific. And for this purpose, yeah, I'm actually considering training an LLM so that it would be following like chemistry related tasks better.
Okay. So for example, when you use the RAG, does it actually remove almost all possibilities of having hallucinations or fake information in the output?
I wouldn't say 100% removed, but mostly removed. I did experience, like as an example, with like Cloud 3.5 Sonnet, I actually experienced hallucination doing RAG from like a predefined PDF. So it's not like you can always remove it, but you can reduce it. And if you, so for the Eunomia package, we do actually have the paper. It's published on Digital Discovery. We did a lot of benchmarks to make sure that with the iterative chain of verification, we can actually remove the chances of hallucination, in a sense that if the sentence is actually talking about like thermal stability, and we care about water stability property, we would have that point removed, like the agent would iteratively update its own reasoning. Kind of like a sanity check, you can think of it.
Okay. Okay, thank you so much.
Yeah.
I have a question about, LLMs offer a lot of benefits for incorporating domain knowledge in terms of flexibility, probably is the biggest one, of just and ease of use, language as sort of being able to represent anything in some ways sort of inherently. Versus, more traditional informed machine learning, feature engineering, symmetry-aware architectures, physics-informed losses. What do you think are the big, downsides to the LLM approach, and do you see any hybrid approaches in the future?
Sure. So I feel like LLMs have been applied to very different applications, and maybe right after the start, when they're being hyped, people started to like fine tune them for different downstream tasks. But the thing was that I wasn't sure why people are doing that, and the reason is that I feel like fine tuning like a billion parameter model that a simple machine learning model, or not even machine learning model, like a deep learning model can do, it's more of an overkill. So I would say, some people still do that. Maybe maybe the trade-off makes sense. Like maybe the performance is just a little bit better. Not sure if that's viable or not. But in a sense that how they can be used, I'm very much optimistic about the like the reasoning models that are starting to appear, and essentially having an intelligent orchestrator that can deal with natural language text is really helpful for our daily activities, not just in the realm of chemistry. But in our world, I would say I'm very much interested in the idea of AI agents, and have them augmented with those tools. This is mostly because of the fact that within the community, we can actually use different tools being developed by other people. So you don't necessarily have to work on like primarily fine-tuning an LLM for just doing one task, but have it augmented with your desired tool, and that could come from some other people's work. So that would be like a win, I think. I hope that answers your question.
Yeah, I think that answered the question of just how can we bring both approaches together.
Mm-hmm.
If there is no other question, I would like to ask.
Sorry, I have one question in the
yeah,
chat.
please do. Please do.
Oh, I'm just reading it now. Clarify, there is LLM to handle domain knowledge search and human interaction, and a separate non-LLM model to use domain knowledge to generate output. No, this is interacted within one agent, so essentially one LLM. And technically you're right for one part of it, but So we can use different LLMs within the workflow, in a sense that, let's say one LLM is really good at reasoning. We can actually use that to derive the agent. One LLM is really good at doing RAG. We could actually use that for doing the RAG. And yes, the non-LLM model is essentially like a physics-based model or like a surrogate model that can make prediction for the property of interest in the example I just showed you. And that incorporates essentially the domain knowledge. Hope that answers the question. Great.
Yeah, so I wanted to know what LLM are you specifically using? Are you using GPT-3, or are you using BERT? And the RAG that you use, is it open source, or which one are you using?
So for me, I'm using different ones. Been using DeepSeek R1 a little bit, but currently it's like a mixture between like open source and closed source LLMs. And one idea is that with like an open source LLM, you can actually get the probability of the output token. So you can actually use it in like Bayesian optimization algorithms and do a lot of like cool things with it, since you have access to that information. But for the decision making, still you can actually use like methods with like open source LLM, like partially observable Markov decision processes, so that you would actually use a smaller LLM, but define like a probabilistic algorithm so that the model can do better decision making based on the feedback it gets.
So we are right at time. We are right on time. So if there's no more question, we can call it a day. Yeah, and thank you
Okay.
guys. Thank you, Mehrad, for this really interesting discussion. And yeah, thank you all.
Okay. Thank you, everyone. Have a great day.